Okay, now we have seen that alpha-beta pruning can essentially make our adversarial tree search more effective, but it's not good enough. So what else can we do? In realistic games, you can't even reach the leaves, even with doubled, effective search depth. And that's why we sort of considered something from the previous topic, search, where we had iterative deepening, which is a basically depth limited search. And here we're considering that too. And what do we do when we reach our search depth? We basically replace the nodes with utility nodes by using an evaluation function. So if you look at the example on the right, we limit our search to be after one turn of the max agent and min agent. And after that, we just use an evaluation function to estimate the utility of the nodes and treat them as terminal positions. And for example, so how much does this increase our resource search depth? Suppose we have 100 seconds to make a decision, and we can export 10K nodes per second. So we can check 1 million nodes per move. And alpha-beta pruning can bring down the depth to about 8. So this can essentially be used to play chess. However, there's some limitations. If you actually use the evaluation function to approximate the terminal states, the optimality guarantee is gone because you're estimating stuff. And moreover, if you increase the depth, it makes a big difference, but it will also cause a lot of computational resource. Last but not the least, some people choose to use the iterative deepening method.
So this is basically when you have to return within a given time frame instead of a given depth. So basically, you will search deeper if you have more time, and if you need to return any point, then you will just get the best results so far.
Yeah, that makes sense.
All right, so let's take a look at what happens when we limit the depth to 2. So we have this Pac-Man here, and the objective is to eat both dots in this particular maze. And let's see what happens when we call the evaluation function at depth equals to 2. So it's currently the Pac-Man is still calculating. Let's see. All right. So it makes a move that's in the right direction, but then it goes to the left, goes back to the right, left, right. It just basically, just iterate, it just oscillate back and forth instead of, eating any of the dots. So, this is basically, you might ask, okay, what's the problem? Like, why do we have this kind of behavior? Yeah, so the reason this might have happened with d equals to 2 is, can be illustrated in this particular diagram here. So this is where Pac-Man started in this mini grid. When it goes left, it eats a dot. It's good. It received a reward. But when it goes right, it basically doesn't eat anything. And then from the left-hand side, the Pac-Man can also move the other direction, which basically does nothing. And on the right-hand side, the Pac-Man can either move into another empty square or you can eat the dot. So basically, let's say eating the dot, gives, value of 10, right? So both this state and this state is going to have value of 10. But let's say this state here will have a value of 0 because the Pac-Man basically didn't do anything. So if you look at what value would this state get? Well, in the single agent search, this state will also get a value of 10, and the state over here will also get the value of 10 because it's taking the max between 0 and 10. So then, from the root node's perspective, moving left and moving right is exactly the same because they both have value 10. But the reality is, if you choose to move right, there are, this particular scenario that the agent can fall into, which is basically the same state as it started with, but it actually is worse off. So basically, that's why this oscillation behavior can arise. It's because the agent will go here, and in this case, you can imagine, the scenario is flipped and it goes to the others, the symmetric game state, and then you would just go back and forth, because it couldn't differentiate between, the potential of getting more reward versus, getting more reward directly versus, a state that could give you more reward.
Yeah, and that's the issue of the evaluation function essentially, because the evaluation function gives the same utility for these two configurations, whereas in reality, the left one is apparently better because it is actually one step closer to the other dot. So let's say if we increase this utility function to 11, this value becomes 11, and Pac-Man will go to this configuration for sure. And then after replanning, it will finish eating all the dots.
All right.
All right, let me clear my drawings. All right, let's take a look at the Pac-Man with the better evaluation function.
So here's that same configuration, still looking ahead too, but now the truncation function is score, but you get increasing credit for being closer to a dot. So now we take the same first step, but now we go straight to the end and don't thrash. Many of you will see thrashing in your projects. When you see thrashing, it is usually not a bug in Minimax. It's usually a deficiency in your evaluation function.
Yeah, so as Professor Dan Klein suggested, if you ever encounter that in projects, write a better evaluation function.